Hello everyone. So today let's solve the problem. This one, Team Rocket arises again, right? So this was asked in the Codecraft-17 and Codeforces around 391, right? So division 1 for the division 1 and the division 2 combined, right? So you can just go through the question. It's easier to understand. Now let me summarize the question so that it will be easier for us to solve the problem, right? So let's see what the question states here. 1 second. Yeah. So now here there are n cities, right? So the question name is Team Rocket Rises Again, right? So this is basically based on Pokemon, I think. I don't know. So yeah, Team Rocket, two, one guy and a girl used to be there, right? Yeah, along with the this one, who are against the Ash, Brock, and Misty, if I remember correctly. The names. Team Rocket. Yeah, they were against the this one, Ash, Brock, and Misty, I believe. Yeah, if I'm correct. One of my favorite shows, actually. Yeah, this is fine. Let's move on with the question. Let me delete this one. Yeah, let's see what the question states here. Right. So there are n n cities and m weighted. This one m weighted undirected roads. There are n cities and m weighted undirected roads. Right. There is a guy named Bash who lives in the city S. There is a guy named Bash who lived who lives in the city S, right? And sends a gift to he sends a gift to every reachable city along the shortest path. He sends a gift to every reachable city along the shortest path, right? So Team Rocket can destroy. So there also they used to destroy the Ash team, right? So here Team Rocket can destroy exactly one other city, right? So the Team Rocket can destroy, I'll just write it over here. Team Rocket can destroy exactly one city, right? Exactly one city, meaning removing it and its incident edges, right? So Team Rocket can destroy exactly one other city just to maximize the number of friends whose arrival time strictly increases. Whose arrival time strictly increases. Then what we need to do? We have to output the maximum number of unhappy friends. We have to output the maximum number of unhappy friends after destroying one city. Again, what we need to output here? We need to output maximum number of unhappy friends, right? So yeah, let me give here. We have to output maximum number of unhappy friends after destroying one city. After destroying one city. That's what we need to do. Our job is to output the maximum number of unhappy friends after destroying one city. Right. So let me read the question loud. So just listen to this carefully. There are n cities and m weighted undirected roads. Bash lives in a city S, right? So a guy named Bash lives in the city S and he sends the gift to every reachable city along the shortest paths, right? Reachable city along the shortest paths. So Team Rocket can destroy exactly this one. What do we call? Exactly one other city just to maximize the number of friends whose arrival time strictly increases, right? So, or die while waiting, right? So what we need to output here, we have to output the maximum number of unhappy friends after destroying one city, right? So let me delete this one. Yeah, let me come to the input output here, right? So this is nothing but the n here, right? So accordingly with the question that we discussed here, we have n cities and m unweighted, just right? So this is nothing but n number of nodes. So 1, 2, 3, 4. You can just count it here. See here, we have number of nodes is 1, 2, 3, 4. So this is nothing but n. This is nothing but m. M is nothing but the weighted undirected roads. We have 4 here. That also you can see, right? So weights, basically this is fine. This 3, I believe this is s, right? So this is s basically, right? So this is fine, man. Now what are these? Basically these are edges. These are edges along with the weight. So edge 1 2 is having the weight 1, edge 2 3 is having the weight 1, edge 2 4 we are having the weight 1, edge 3 1 we are having the weight 1. So these are the edges. So edge 1 2 is having the weight 1. Same thing goes with first one as well, right? Yeah, first two numbers are the edges and the third number is the weight, right? So you can just draw the graph. They have shown the graph here. Have they? Uh, they haven't. So you can just draw the graph for the edge basically from 1 to 2. So I'll just draw this one instead here just to show you. So I always leave you to draw the graph basically. So this is fine. 1 to 2. So we have the weight 1. 2 to 3 we can just draw in this way, undirected graph, right? So 2 to 3 we have the weight 1 here. Again 2 to 4 we have, so I'll just keep here 2 to 4. This is fine. So we are having the weight 1 here as well, and 3 to 1 we have, right? So 3 to 1 we have, uh, 3 to 1 we have, right? So let me write here itself. 2 to 4 we have the weight 1, and we have 3 to 1, right? So 3 to 1, you can just write it over here. So this is also having the edge 1, right? So this is this one weight 1, right? This is fine, man. So this is the graph actually, undirected graph they have shown, right? So 1 to 2 with the edge 1, 2 to 3 with the edge 1, 2 to 4 with the edge 1, sorry, weight 1, 2 to 3 with the weight 1, this one 2 to 4 with the weight 1, and 3 to 1 with the weight 1. So the output that we need to get here is 2, meaning the maximum number of unhappy friends after destroying one city is 2 here, right? Same goes with the example or the input 2 as well. In this case, we have to get the output 4. I believe this is fine, man. Let me delete this one entirely. Now, we have the understanding of the question. Now we have the understanding of the question. And one more thing, now we are having the idea on the input output as well. Let's do one thing. Let's quickly discuss the approach followed by the complexities, and then let's write the code. First, as usual, let's discuss the approach first. So here I have considered the same first example that they have shown in the this one question, right? So we have already discussed this one actually, and this is actually S. So these are the edges, and this is the weight, right? So we know this. So output that we need to get here is 2, the maximum number of unhappy friends after removing one city, right? So this destroying one city, right? So this is fine. So first thing I want to tell you here is we will be going with a Dijkstra to solve this particular problem, right? So let's move on with a step-by-step explanation. So same thing, and for so this is fine. We know this one already. Now, first step, what we will do here, we'll be considering the same first example, man. Not to worry, right? So here we will be running the Dijkstra from s equals 3. So we have s3, right? So they have given s equals 3, the point from where we have to find the shortest path. We will run the Dijkstra from s equals 3 to compute distance, nothing but the shortest distance. So there will be one node they have to give at least to compute the shortest distance. Whenever if they have given, then we can go with either Dijkstra, Bellman-Ford, anything, right? So they have given here s equals 3. So we will run the Dijkstra from s equals to 3 to compute distance, nothing but the shortest distances here. Distance of 3, we have 0. Distance of 2, we have 1. Distance of 1, accordingly with the graph that I had written basically, right? So you can just check the graph. You can just rewind the video. You can just go there and you can just check the graph, right? So distance from s equals 3 we are considering, right? So distance of 3 initially it will be 0. Distance of 2 from 3 it will be 1. Distance of 1 will be 1. Distance of 4 we have to go from one node to another node. So that will be via 2. That will be via 2, right? So let me write it over here itself. One second. This is not writing. Yeah, 1. So this one will be 1 to 2. 2 to 3. I can just write it over here. 2 to 4 as well, and 3 to 1. So 2 to this one actually, 1 to 2, 1. So all 1, right? So this is fine. So now, basically, we are going from this one. We are calculating the shortest distance from this node, 3 actually. S equals 3 we have been given, right? Shortest distances, basically, distance of 3 initially, this one, initially we will be setting this one to 0. Distance of 2 from here to here, 3 to 2. So this is 1, right? So this is fine, 0, 1. Distance of 1. So from 3 to 1 we are going, right? So this one we have to consider. So this is also 1. So distance of 4 we have to go. So for the distance of 4, we have to go from here basically, right? So just give me a second. Let me show you here. This one with this color itself. First, we have to go to 2. Then via 2, we have to go to 4. So this one will be 1 along with this one. So this will lead to 1 plus 1. So this will lead to 1 plus 1, nothing but 2. Nothing but 2. So distance of 4 is 2 here. Distance of 1 is 1 and distance of 2 is 1. Distance of 3 initially this will be set to 0 because we are considering from the distance 3 itself. Again, I am telling, if you don't know the Dijkstra algorithm, very recently we have discussed that one in the graph based algorithms playlist. You can just go there and check. You can just check the Dijkstra algorithm. If you don't know Dijkstra, Bellman-Ford, Floyd-Warshall, this one Johnson's, this one Kruskal's, Prim's algorithm. If you don't know, you can just go and check that playlist, right? So then you can come back and you'll understand this one very clearly, right? So this is fine. Now let's move on with the next step, right? So this is fine. So next what we will do, we'll build the shortest path DAG, right? So we'll be building the shortest path DAG. So for every edge UV, if the distance of u plus w, nothing but at this one u plus w is nothing but the weight, this is equivalent to the distance of v, right? So we will be adding here this one u to v. We'll be adding, yes, u to v, right? So for example, 3 to 2, from 3 to 1 and 2 to 4, from 3 to 2. So you can just look at the graph, 3 to 2, 3 to 1. So this one 3 to 2, 3 to 1, this one itself again. So let me mark, let me write it over here. Just give me a second. What happened to this pen? 1 second. For example, 3 to 2 I have shown you. 1 second. So yeah, this one 3 to 1, this path. And finally here 2 to 4, right? So 2 to 4 is nothing but here itself, this one again, right? So this one basically, right? Yep. Now let's move on with the next step. So we have to count for each vertex v how many nodes must go through the v. So obviously we have to count for each vertex how many nodes must go through that particular vertex v, right? Uniquely on all the shortest paths from S. So we do this one by topological style propagation, right? So if you don't know topological style, so that one also we'll be discussing today actually, right? So we don't have to worry. So we'll be discussing this one topological sort, right? Kahan's algorithm basically. So we do this by topological style propagation on the DAG, right? So what we will do, we will propagate component ID. So we will be propagating component ID. This you will understand when we write the code clearly, man, this step, right? So if a node has multiple candidate sources, it becomes ambiguous, right? So if the node has multiple candidate sources, so in our case, we don't have, for the input that we have considered, we don't have to worry, it becomes ambiguous, right? So size of ID, let's move on with the next step. Size of ID stores how many targets depend uniquely on that particular node, So destroying the node with maximum size, including S, yields the maximum unhappy friends, right? So destroying the node with maximum size, nothing but excluding the S part, excluding the S, right? So as we have considered the node 3 in our case. So destroying the node with maximum size yields the maximum unhappy friends. In the example, node 2 uniquely controls node 2 and 4, right? So we had to move to this one from 4 to 2, this one, I forgot, man. Just give me a second here. Node 3 to 4 and yeah, 3 to 2 and 2 to 4. 3 to 2, first 3, then we have to move to 2, then from the node 2 to we had to move 4, move to node 4 basically, right? So in the example, node 2, this one, it uniquely controls node 2 and 4, right? So therefore the answer that we have to go with here is 2, right? Meaning here the maximum unhappy friends after destroying one city will be basically 2. This one is easy to understand, right? So yeah, answer that we got here is 2. Simple, right? The output that we got here is 2, which is equivalent to the output that they have mentioned for the example within the question, right? So our approach works absolutely correct in this case. Our approach works absolutely correct in this case, right? Now, as we are completely familiar with the approach, let's move on with the complexities part. So what will be the time complexity here? The time complexity would yield to big of m log n. So why it is big of m log n here? Because Dijkstra dominates, basically why it dominates, we will be making use of the priority queue, right? So if you remember, we'll be going with the relaxation step, right? Priority queue relaxations we'll be going with. After writing the helper method Dijkstra, usually we'll at the end we'll be going with the priority queue relaxations, right? Dijkstra dominates here. Plus, because of m plus 1, it will be to build and traverse the shortest path DAG, right? So overall time complexity would lead to because of m log n, right? So what will be the space complexity here? The space complexity would lead to big of n plus m, because we will be making use of the, as usual, we'll be going with the adjacency list and this one, some other arrays, auxiliary arrays we can consider, right? So whether it may be distance, id, temporary, size, this one d, for the distance d, and this one as well, visited also we have to go with, right? Visited array as well. So instead I'll just say here auxiliary arrays, right? So we'll be going with the adjacency list and the auxiliary array. So overall space complexity would lead to big of n plus m. The time complexity and the space complexity for the code that we'll be writing in the future would be big of m log n and big of n plus m respectively, right? So now as we are completely familiar with the approach and the complexities, we are good to write the code. Let's start writing the code. So let's start writing the code here. So I'll just come here. This is fine. Now let's do one thing. We'll be going with a fast input and the output along with the different utilities. So let me import input output package along with the this one util package as well, right? So utility package this is fine. Let's make use of the class main. I'll just give the name main as usual. So I can just give any name that's relevant to the question. First, let's go with the maximum array size. All right. So let's go accordingly with the constraints man. So this is safe upper bound for n up to 2e5. We can consider, right? 2 into 10 to the power of 5, I'm saying. So this is, we have considered a bit extra for the safety here. So I'll just go with here, as I've said, I'll just go with static final int equals. So let me go with int n equals 6 followed by 3 zeros 1 0, right? So this is fine man. Now let's go with the graph parameters here. I'll just go with static int n comma m s. This is fine. Now let's go with the d. This is used later, but this is but left as in the original code, right? So we'll be going with a distance dis, which stores the shortest distance from the s, right? So d and the distance, d is nothing but it is not used later but left as an original code, but distance dis variable, right? So these two things will be initializing. Now this stores the shortest distances from the s. Just remember this one carefully. So this one will be static uh nm as we have went with, so d and dis we have to go with, right? So this one is d, along with a d have to go with new long, we have to assign this one to the new long of size, and also distance equals new long of this one again size. And this is fine. Now let's go with a visited array for the Dijkstra. When I say visited array for the Dijkstra, let me go with static here. This one is fine. Boolean, yes, visited equals new Boolean of this one, and this is fine. Yep. Now let's do one thing. Yep. After this, we have to go with the adjacency list, right? So let me go with the variable e for this, for the original weighted undirected graph, right? So let me go with your static list, yeah, int. We provide array here. So again, one more array outside the variable e, as I've said, new. Just I didn't make use of the array list till now, right? So this is, let me type this one entirely. Yep, new array list of, oh, this one has to be size and one. One second. This is fine. Now let's do one thing. Let's go with the adjacency list for the DAG of the shortest paths, nothing but the for the directed actually. So this one is static list integer provide array g equals new array list of n again. So this is also fine. Now we need ID as well. So I'll just go with static here. So this one int ID equals new int of n, also size equals, so this one new int of this one n. Yep. Finally, also we need temporary variable. So this one I'll just call tmp here. New int of, let me assign this one to the size n. Now this is fine, man. Let's do one thing. Let's go with the distra just to compute the distance from the source s. Right. So this one will be static void distra. Right. So this is fine. So within the distra helper method, so we are just going with the distra just to compute the distance from the sources, as I've said, right? Uh, this is fine. A source S in the sense S they have, I had shown you by considering the first example, right? In our case, S was 3 for the first example that we considered for the approach, if you remember, right? So let's initialize the distances to a very large value. So I'll just go with arrays dot fill here. So this one will be distance, comma. We are assigning this one to the large value, right? So I'll just go with max underscore value. Yeah, this is fine. By 2. Yep. The next step would be, let's go with the priority queue. Distra uses priority queue. We know this. Let's go with the priority queue of pairs, right? So in this case, the this one pairs are nothing but the distance and the node ordered by the distance, right? So let me go with priority queue here. This is fine. Yeah, let me go with a long. So yep, this is fine. Q equals new priority queue. So let me go with comparator here. Comparable comparator. This is fine. Dot comparing what we need to comparing here. What we need to compare, sorry, here. Comparing long. This is fine. A, let me make use of the lambda here. A of 0. This is fine. Yeah. Yep. Now let's do one thing. Let's go with the distance to source. Initially that will be 0. I'll just go with S. Initially 0. Also pq dot add, priority q dot add. So this one will be new long of, this is fine, 0 comma S. This is also fine. Right. So yep. Now after this, what we have to do, let me do one thing. Let's go with the standard distra loop. Right. So as I've said, we have to go with priority queue dot is empty. So we know this one, man. This is not distra within the this one. If you know that, just give me a second, 1 second. Sorry, I was getting a call. So let's continue. So it's fine. Mm, first, what we have to do where I have left. So we went with a standard distra loop, right? So this will be long. Initially, current. Let me set this one to the pq dot poll, right? So this is fine. Yep. This is fine, man. Now let me consider variable x here. So this one will be int of and initially. So this one of 1 basically, right? So this is fine, man. The next step would be we have to skip if already finalized, right? So if visited of we have already visited the x, then we have to skip that. So we are just going with a this one continue. We have visit that particular node already, then we have to skip that one, right? So then we have to set the visited of x equals to boolean value true, right? So this is fine. It's easy. Now we have to relax all the edges from x basically, right? So let's go with a for loop, nothing but the iteration here, int ed of e of x. This is fine. What we'll be doing within the for loop. So I'll just go with int y equals of 0. This is fine. W equals ed of 1. This is also fine. If distance of y If it is greater than distance of x, then what we will do? Plus w we have to go with the weights as well, right? Sorry, not one w. Right. So we have found a shorter path to y via x in that case, right? So I'll just go with the distance of y. Let me assign this one to, one second, distance of x plus weight, nothing but w in our case. So it will be priority queue dot add. What we need to add? New long of, sorry, your array we have to mention. Then we have to go with a square, this one flower bracket, right? So we have to pass distance of y along with the this one y. This is fine. Yep. Let me give semicolon here. This is also fine, man. Yeah. Now let me come out of this one entirely, right? Oh, how many places are here, man? This one, right? So I have already left the space. Thank God. This is fine. Yep. Now let's go with the main method. We have successfully written the distress helper method, right? So we know this one. So again, I'm telling, again, I'm repeating. If you don't know the distress algorithm, recently we have discussed in the this one graph-based algorithm playlist, right? It is found in the graph-based algorithms playlist. You can just go and check there. So only thing is, uh, only difference is we have discussed that one with the help of the programming language. It's written in the programming language Python, right? So this one will be same. Explanation will be same. You can just go through it. You'll understand, right? So this is fine. Now let's go with the main method. So this is fine. Let me remove this one and let me go with throws exception, right? So within the main method, let's do one thing. Let's go with the fast input and the output setup, right? So just give me a second. So I'll do one thing. So let me copy paste this one, right? So this is purely related to the input output, not the logical part. So we have made use of the buffer data for the fast input, print data for the fast output, basically string tokenizer. And again, this one, we have to pass the numbers that is given in the form of integers, right? So nm and s, this one, basically 443711 to the first line. So that's what I have done. All are integers, right? So we have went with integer dot pass and string tokenizer dot next one. This is fine. Yeah. Now let's do one thing. Let's continue with the next thing. So let's read the first line nm and s. So this is also related to the. So we have done this one already, right? So now we have to initialize the adjacency list for 0 to n, right? So we will be making use of one base nodes here, right? Just remember, we'll be making use of one base node. So let's go with the iteration part. Let's move on with the iteration part. I equals 0, I less than n here. So we have to go with I less than or equal to n, right? Yeah. Within the for loop, so this one will be e of I. Let me assign this one to the new array list. So this is fine. Yeah. Now g of I, this one is also fine. New array list. Yeah, this is also fine. Let me come out of this one entirely. Now, let's do one thing. We have to read M undirected graph edges and add that one to the adjacency list E. We know this one, right? So exactly what we had this one discussed in the approach, the same thing we are articulating in the form of code. What we have to do now, we have to read M undirected weighted edges and add that one to the adjacency list E, right? So let's go with a for loop here. For int I equals 0 again. I less than m this time. Let me go with a I plus plus. So first string tokenizer here, new string tokenizer. So this one will be buffer reader dot read line. So this is also fine. The next thing would be we'll be going with a x, y, and w, right? So x, y, and w. So let me copy the same thing here, nm and s, and then we can this one change this one, right? So one more thing here. Yeah, let's do one thing. Let me paste it over here. 1 second. So this is fine, man. Let me go with the int here. This is fine. Also, let me go with int here as well. And finally, let me go with int here as well. So integer, instead of n, this will be x. Instead of this one will be y. Instead of s, it will be x, y, and u, right? So this remains integer dot percent, or everything is of the type int itself, right? We have not made use of the long. This is fine. Yeah. Now let's do one thing. Now as we are going with the adjacency list, so we are reading the m undirected weighted edges and adding that one to the adjacency. This one adjacency list e. So now we have to add that one to the adjacency list e, right? So this one will be e of x dot add of new int. So this is fine. Yep. Now let me go with y comma x. So this is fine. We have to keep this is fine, right? So let me copy the same thing and make the necessary changes for y. So this has to be e of y dot add new int of this one. Instead of yw, we went with a y. We have to go with a yw, man. I believe, right? So y and weight we have to go with, right? So this one has to be x and w, right? So just give me a second. I'm just getting a call. Just give me a second here. Sorry, I got a call again. So now let's move forward. So we are done with this, right? So we are done with this part basically. Are successful in reading the M undirected graph, M undirected weighted edges and adding that one to the adjacency list E that we have done. We are done with that part. Now let's do one thing. We have to compute the shortest distances from S, right? So that they have strictly mentioned in the question. We know this one, right? From the approach actually. We just go with dij. Dij is the this one, right? So we are making use of this helper method within the main method. Dij, we just have to call the helper method here, right? So now this is fine. Next step is we have to build the shortest path DAG, right? So we have to build the shortest path DAG here, right? Let's do that one. Let's go with a for loop here. For x equals 1, x less than or equal to n, x plus plus. So this is fine. Yeah. Now, one second. Fine. No need of this one, I believe. Lar bracket. So I'll just go with for int individual edge of e of x basically. This is fine. Now within this for loop, let me go with variable y and assign this one to the edge of 0. And also weight, let me assign this one to the edge of 1. So this is fine, 0 to 1. So now let's write the simple if condition here. If distance of x actually, distance of x plus weight w, if it is equivalent to the, sorry, if it is equivalent to the distance of y, then what we need to do here, mm, distance of, sorry, g of x. So this one dot add of y, dot add of y. So this is also fine. Now d of y, let me increment this one, right? So let me come out of this one entirely. Now let's do one thing. Yeah, let's initialize the temp of I that is equivalent to the I. So here each node initially proposes itself as a unique candidate, right? So let's go with a for loop here. This one int I equals 1, I less than or equal to n. So let me go with I plus plus. This one temp of I equivalent to the I. This is fine. Now let's do one thing. Let's go with a queue for Kahan like this one topological order starting from the source S, right? So this one, let me go with a queue actually. Queue similar to the topological sorting like thing we'll be going with, right? So this one integer, let me go with a variable q here, new array dq, right? So this one, why did I leave space here? Array dq. Yeah. Now let's do one thing. Yeah, this is fine. We have to add s to the queue, right? So this is fine. Next, what shall we do? Let's go with the this one, BFS or the topological propagation on the shortest path DAG, right? So what's the purpose here of making use of the BFS or the topological propagation? So here we have to determine for each reachable node whether all the shortest paths from S to that particular node, right? S to that particular node come through the same first branch node, nothing but the component ID. Otherwise we have to mark ambiguous. This we know from the approach, right? Otherwise we have to mark that one as ambiguous, nothing but -1 in our case, right? So this is given in the question itself. Now let's go with a standard this one BFS loop. So I'll just go with q dot is empty here. This is fine. Within the while loop, what we will be doing? So int x equals q dot poll. So this is fine. Yeah. Now let's do one thing. We have to assign ID of x, nothing but if the temp of x is a valid candidate, not -1 and not s. We have to use temp of x, right? So that's what we need to do. Else, we have to just display x. So let me write that this one in the form of code. So this one will be ID of x equals temp. So this is a bit of headache, man. Yeah, -1 basically. This is fine. This is kind of difficult to implement, even though if you know this one and all, graph and all, this one will be stuck with somewhere, right? Uh, so we have to go with the topological sorting like structure or the BFS standard loop that we have mentioned, right? So we might get stuck here while this one. This will take hell lot of time while implementation if you are implementing. So without the internet, I'm saying, right? So if you are trying to implement on the same, right, this is fine. Mhm. And of x basically this one, if it is not equal to s, then we have to display basically hmm, temp of x. Else let's just display the x. This is fine, man. Next one, what we need to do, we have to increment the size of the component, nothing but id of x. This counts the nodes that are uniquely controlled, right? So I can just write it on this way. This is simple size of id of x. This is fine. Of x, let me increment this one. So this is fine. Now we are almost at the end basically for this one, whatever we have going with, right? So we have to propagate the ID information to the children in DAG. So let's move on with the iteration here. This one in y of g of x. This is fine. So if the child y still has its initial temp of y that values, if it is equivalent to the y, then we have to accept the current ID as its candidate, right? So let's write the simple if condition. Yeah, let's write the if condition for that one, right? So this one will be temp of y. If it is equivalent to the y, then let's go with tmp of y equals id of x. This is fine, man. Else if, so this one temp of y basically, this one if it is not equivalent to the id of x, right? Id of x, then temp of y, let's assign this one to the -1. Let's assign this one to the -1. Then we have to decrement in degree, right? So then we have to decrement the in degree 1 0, and also we have to push that one to the q. Let me write simple if condition here. Dy, so this is fine. D of y, right? So not the dy basically. Yeah. Uh, the value is equivalent to 0, then we have to add that one to the queue. We have to add y to the queue, right? So this is fine. Yep, we are done with this part. Let me come out of this one entirely. Now we are left with only one thing, nothing but we have to find the maximum size of I and overall nodes. If I, when I not equivalent to the S, right? So that is the best city to destroy to the maximum unhappy friends, right? To maximize this one. What do we call? That is the best city to destroy to maximize unhappy friends. So first let's go with the resulting variable. We have to store the solution somewhere, right? So I'll just go with the ANS here, nothing but the answer. Let me go with 0 here. Initialize this one to 0. Next, the for loop int I equals 1 I less than or equal to n I plus plus. So this is fine. If I not equal to s, then let me go with the answer variable. So equals math dot max of this is fine. Let me go with answer, comma size of I. Yeah, the final one is we have to output the result, man. We have to output the result. So I'll just go with out dot println. Let me pass the answer variable here, and also let me give here out dot flush dot flush. Just you can just go with out dot close or out dot flush. Anything works here. So we are done with the code. So this is it for the code. So this is really difficult one to implement. I won't lie. So only Dijkstra, if we are going with only Dijkstra, this is fine. Actually, you can just implement the Dijkstra in an easy way. So other stuff, the initialization part, so you have to go with the constraints and other part. And again here, topological sorting kind of structure. So we went with the BFS and the Q, right? So this one, so this is really hard to implement. I wouldn't like. So yeah, and if you're doing without internet, this is literally hard. I wouldn't like. So now let's do one thing. Yeah, before checking the code with the different inputs, let me copy paste the signature starter template. Just give me a second here. Let me paste this one over here. Now let me come to the question. Let me copy this one entirely. So the output that we need to get here is 2 for the first one, right? We have discussed the same thing within the this one approach. Now we have some errors. How many errors we have, man? Oh, 7 errors we have. So first one, cannot find the symbol. This one has to be capital I, line number 28. So I'll just come here. Where is this? Where is this? Yeah. Let me give capital I here. Let me run this one. Yep, we are left with 6 errors still. So this is warning. This is also warning. Let's leave this. Let's start from here. Error cannot find the symbol. Y comma W. W cannot find the symbol. Where? Line number 75. So we are going with a weight here. Mm, X, Y, along with the X, Y, we need to have the W or what? Right? So this one has to be W itself, right? So I have given U. So that is the reason it is saying this one. Cannot find the symbol. Yeah. Now we are left with 4 errors. Sorry. This one error cannot find the symbol. I. Oh yeah, here double I have considered here. Number 93. Typos everywhere. Yeah. Let me run this one again. Yeah, we are getting the correct output too, right? So you can just ignore the warnings, man. This runs correctly in the Codeforces environment. So this is fine. So let me copy this one entirely. Now we have to get the output 4. Let's check the same. So just copy this one. Yeah, let me run this one. Yep, we are getting the output 4, which is absolutely correct, basically. So let me copy this one, this code actually. We come to the question, submit this one. Yeah, let me paste this one, right? And hit the submit button. Let's wait for some time. How many test cases are there, man? So many test cases. Yeah. 121 plus. Oh, 150 plus test cases we have. So here you can clearly see in the toast it is showing accepted, right? So the verdict that we got here is accepted. Again, we have went with a Dijkstra to solve this particular problem, right? So Dijkstra's algorithm to solve this particular problem along with the BFS, right? Topological sort kind of structure we have went with. So mainly the BFS, I wouldn't lie here. This one you can clearly see the standard BFS loop. Right? This is structure somewhat similar to the this one topological sort Kahan's algorithm, if you know, right? So we haven't discussed that one yet. We'll be discussing that one in the future as well. So you can just check the graph, this one algorithms if you don't know certain algorithms, right? So you'll not understand while we solve the problems if you don't know. If you know, it is better. You don't have to go there and learn the algorithm. If you don't know anything, then you can just check the algorithm, man. It's very easy to understand, right? So now this is it for the solution basically. I hope the solution part is completely clear along with the approach and the complexities. For now, this is it. Thanks for watching, guys.